You see AI creating these incredible, stunning images all the time. But have you ever really stopped to wonder how it goes from a screen of just pure static into a masterpiece? Well, today we're going to pull back that curtain and look at the magic of what's called flow-based AI.
So yeah, this is the big question, right? How do you take a screen full of random noise, I mean literally just digital static, and actually teach a machine to turn it into something coherent, something you or I would recognize? We are about to dig into one of the most elegant answers to that exact question.
Okay, so imagine our starting point is just a cloud of random dots. They're just scattered all over a canvas. There's no structure here, no pattern, definitely no meaning. It's pure chaos. It's basically the computational version of a totally blank slate.
Now, from that chaos, our goal is to learn a transformation. We need a set of rules that can take that messy cloud of points and gently, smoothly guide every single one of them into a specific, organized shape. In this example, what we're aiming for is that classic moons dataset. We're literally turning randomness into a clear pattern.
So how in the world do we define this transformation? Well, instead of thinking about it as one big, jarring jump from noise to an image, what if we imagined it as a continuous, smooth flow? You know, kind of like particles just drifting along in a river. To describe our river, we're going to need a map of its currents, and that map is what's called a vector field. At every single point in our space, the vector field tells us which way the water is flowing and how fast it's moving. So every single one of our random dots is now like a little particle in this river, and the vector field is its guide.
And the mathematical rulebook for this entire journey? Well, that's an ordinary differential equation, or an ODE. It's this really powerful tool that describes how something changes over time. For us, it's basically the physics of our digital river, telling us exactly how our particles are supposed to move.
Okay, so this sounds great in theory, but in the real world, the vector fields you need to create really complex images are, well, they're incredibly complicated. You can't just solve the ODE with a nice, neat, perfect formula. So what do you do when the math gets that messy?
We approximate. We use something called a numerical solver. So instead of finding the exact continuous path, we start at our random point, we check the vector field to see which way to go, we take a tiny little step, and then we just do it again, and again, and again. It's like navigating a river by taking thousands of tiny little paddles, constantly adjusting your course based on the current right where you are.
So we know how to follow a current if we have the map. But how do we design the perfect map, the perfect vector field that takes random noise and turns it into the exact image we want?
This is where the AI really comes into play. We don't have to design that vector field by hand. We actually train a neural network to do it for us. The network basically learns to become our dynamic map maker. You give it any particle's position and a point in time, and it spits out exactly where that particle should go next.
And this right here, this is the core concept of a neural ODE. It's not a network with a fixed number of layers. It's a network that defines a continuous flow. It learns the very physics of the transformation, creating a vector field that can sculpt any starting noise into our final masterpiece. Pretty cool, right?
Now, all of this sounds beautifully elegant in theory, but it's hiding a massive practical challenge. I mean, how do you actually train a network that represents a continuous, infinite flow? The computational cost seems, well, astronomical. Just thinking about it could make a GPU start to sweat. But this is where a little bit of mathematical genius turns what seems impossible into something totally practical.
I mean, really think about it. To train a network using standard methods, like backpropagation, you'd need to calculate how a final error affects every single previous state. For a continuous flow, that means storing every intermediate position of every particle along its entire path. That's practically an infinite amount of data. It's a massive memory bottleneck.
So this is where this wonderfully clever mathematical trick comes in, the adjoint method. Instead of storing that entire forward journey, which is kind of like trying to remember every single footstep you took on a long hike, the adjoint method does something way smarter. It solves a new, related ODE backward in time. It's almost like sending a signal back to your starting point to tell it how to adjust.
This quote just nails it. We only need the final state of our particles to start this backward journey. The backward ODE then calculates all the gradients we need for us as it travels back through time, telling our network how to adjust its parameters without ever needing to store that massive forward path. And the impact here is enormous.
As you can see from this chart, for problems like training a neural network, where you have millions of input parameters but only a single output, the loss, this reverse mode approach is just orders of magnitude more memory efficient. This isn't just a minor speed up, it's the key that makes training these incredibly powerful, continuous models actually feasible on a large scale.
Okay, let's just zoom out for a second and appreciate what we've just walked through. This isn't just some niche technique, it is a fundamental shift in how we can think about creating things with AI. We're moving away from this idea of a rigid, layered assembly line and toward a process of continuous, almost organic transformation. It's a whole new way of looking at it.
So we've gone from a world of discrete, stacked layers to a model of a smooth, continuous transformation. The neural ODE learns the very dynamics of this change. And because it's all based in an ODE, the whole process is perfectly invertible. And that's a huge deal. It means we can run the flow forward to create an image and then run it perfectly backward to get back to the original noise. We have a precise, lossless map between simplicity and complexity.
This is the big idea, right here. We're no longer just applying a series of filters. We are learning a continuous process of creation itself, a smooth, elegant, and completely reversible flow that takes you from simple chaos to complex order.
And this leaves us with a final, really fascinating thought. If we can model the process of artistic creation as a learnable, continuous flow, what other complex systems in our universe could be understood in the exact same way? From the folding of proteins to the evolution of galaxies. Could they all be described by their own unique, learnable flow?